Hello, my name is Areza Javadian Sabat from Politecnico di Milano, and I'm presenting the work entitled Preference Mining in the Travel Domain on behalf of my co-authors Sankari Gopalakrishnan, Matteo Rossi, Fabio Schreiber, and Letizia Tanka. The Right to Rail project is part of the Shift to Rail initiative. Shift to Rail is a joint undertaking funded by the European Commission and by main railways stakeholders. The initiative is aimed at enhancing research activities in the railway sector. Right Rail's overall objective is to develop an innovative framework for intelligent mobility, facilitating the efficient combination of ride-sharing and scheduled transport, thus enhancing the performance of the overall mobility system. The Travel Companion is an application that is being developed to support travelers before, during, and after their trips. The goal of this work is to provide a personalized set of travel offers to users of the Travel Companion based on their context and preferences. The recommender core of the Travel Companion takes as input user data, knowledge models, and service-related information, and accordingly presents a list of travel offers ranked according to the user's contextual preferences. This figure presents the high-level procedure of the proposed ranking mechanism. A new traveler's recommendations will be based on other travelers' historical data with similar profiles and preferences. The system also aims to update the preferences over time. Hence, the solution is to build a recommender system using data mining techniques that provides a knowledge base that will be used along with the travel request to assign a score to each of the candidate travel offers. The scores are then used to rank the offers and provide them to the traveler. The following figure shows the relational schema of the design database. It represents data as a set of related tables. The database includes information about the traveler's profile, past preferences, travel requests, potential travel offers, and characteristics, and the final choice made with each request. It should be noted that the special facility table contains the special features related to each travel offer. For example, special features for persons with reduced mobility. Recommender systems employ rich knowledge base of users' preferences and behavioral characteristics. A knowledge base can be a logical model, or it is built from rules mined from historical data. In this work, we follow the latter. The rules, in turn, can be mined from the user's history or, as in this work, from other users with similar profiles and preferences. The dependency on the existence of historical data is known as the cold start problem. Our system overcomes this by mining association rules from the traveler's dataset. The recommendation has to be handled in multiple situations in the system, and the knowledge base should be accordingly diverse. Also, the representation and the data format of the rules play a vital role in the system's efficiency. The association rules should address both travelers whose preferences are not known or specified and travelers without a past purchasing history to understand their travel choices. The information available from the dataset is a static profile data, travelers' preferences, health issues, travel choices, and facilities of corresponding travel offers. The required format of such rules are as follows. Rule type 1. Profile implies preferences. Given a traveler's profile like age, gender, and occupation, we predict the predefined or in fact the preferred service, meal, etc. Rule type 2. Preferences imply offers. Given a traveler's preferences in the request, we predict their preferred offers based on its facilities. Both rules together cover the significant part of personalizing the travel experience for a traveler. They suggest the possible preferences and possible travel choices that would be essential for a new user. Once the rules type was decided, the next step is to implement the association rule mining on the dataset. The process is composed of the following steps. Table joins along with pre-processing to serve as the input for the algorithm. Generate rules using the algorithm. Visualizing and validating the results. To unify the user's profile and preferences into one table, traveler, travel request, user health, user partner, service preferences, luggage preferences, and meal preferences tables were joined to create one table called user profile. In order to get the user's preferences and travel choices together, traveler, travel request, user health, user partner, service preferences, luggage preferences, meal preferences, travel offer, and offer detail tables were joined to create one table called user offer. The created tables representing the transactions are then fed into the a priori algorithm. Recalling our goal for the system to rank the travel offer such that it is ranked personally for the traveler. To achieve this, we use the rules mined in the previous step to rank the travel offers. The ranking module contains the following steps. At first, compare preferences in the travel request and in the rule antecedents to get the relevant rules. Then use the rule consequence to rank the available travel list by how precise the facilities match. From the mined rules knowledge base, we need to pick out the relevant rules for the travel request. This gives the rules consequence required for the next step. To compare the preferences mentioned in travel requests and preferences present in the rule antecedents, it compares two preference item lists. The cases are as follows. Presence of complete vector. The request preferences are entirely present in the rule. It could be a single item or multiple items, and their order doesn't matter. All the preference items presence implies that the rule is completely relevant and should be picked for the ranking process. Partial presence. The request is partially present in the rule. That is, the rule could include additional preference items, or the request could have additional preference items. Still, the rule is partially relevant and can be picked for the ranking process based on how well they match. An indicator of relevance could be the match level between the preference vectors. Since the order doesn't matter, we need a comparison based on items. The solution is set comparison to retrieve the rules that are relevant to the request. The match level is also valuable for picking only the top few relevant rules for scoring the offers later. For example, for a preference vector like visual vegetarian bag, visual vegetarian implies airplane is a complete match, and pet vegetarian implies walking is a partial match with match level 1. To implement the various comparison scenarios, we need conditions based on which the relevant rules can be retrieved. This compares the rules items from the knowledge base and preferences vector from the request and calculate how well they match. They can be either perfect match, complete presence, or partial match, which their detailed calculation can be found in the paper. The aim is to rank the travel offers that have been received for the current request. The top relevant rules that were picked in the earlier step will provide a set of rule consequences. These are basically suggestions for some facilities that should be present in the travel offers. Moreover, the travel offers should match with the request as well. The traveler, while providing the preferences in the request, can add an additional priority number. This priority is useful in overriding the suggestion provided by the rules, and thus preferences are more personalized than guided by suggestions made from popularity or past history. Hence, the scoring is based on a comparison between rule consequence, preferences given by the user, and facilities in the travel offer. To do so, for each offer, each rule consequent adds a point to matching offer multiplied by confidence. Then, preference vector adds a point to matching offer multiplied by the priority. In the end, it calculates the overall score for ranking. In order to test the proposed system, we need an existing dataset. At first, we attempted to find a suitable publicly available dataset. Although the datasets available had some information about the travelers in Europe and public transport facilities, we encountered some system compatibility issues. As a result, we decided to synthesize our dataset, and the resulting database can be further extended as the users interact with the travel companion. Also, knowing the distribution of the dataset allows us to validate the results. Then we applied the association rule mining. In the end, we tested the ranking mechanism. The following figure presents the graph visualization of the top rules obtained from the experiment. The node size represents support and the color corresponds to the lift. For example, a middle-aged worker traveling for leisure implies bus. A sample run with a travel request and a set of potential travel offers were ranked by the system is shown in the figure. It includes intermediate results of the relevant rules picked from the knowledge base and the final list of ranked offers. The ranking in the example is mainly influenced by the rules mined and stored in the knowledge base. In the end, we have built a prototype to envision the system to understand the user's input and how the results are presented in a personalized manner to suit their requirement. Considering the following scenario, a trip from Milan to Bratislava on October 10, 2020 for leisure. The user has visual disabilities, prefers an airplane, vegetarian meal, and luggage requirements of a bag. The third figure from the left shows the list of travel offers for the travel request made. They are ranked according to the preferences specified by the user and recommendations from the knowledge base. There are some icons depicting the mode of transport, the special facilities available in the offer, if pets are allowed, and so on and so forth. Finally, the most right figure shows more detail on a selected offer. In this work, we presented a solution to build a data mining-based recommender system that provides a ranked list of travel offers filtered and personalized by the user's context and preferences. To test the proposed solution, we synthesized a dataset close to reality. Finally, we demonstrated the user experience through a prototype. It is observed that the solution for the system presented is indeed suitable and can be further explored to enhance its feature set. The rule-based knowledge model's demonstration with the custom dataset shows that the algorithm would continue to learn the user's preferences and provide personalized suggestions on replacing them with actual data. Future work concerns designing personal preference models using supervised learning algorithms. Moreover, we plan to test the system on 4 different European cities. In this slide, you can find the list of references discussed in this presentation. Thanks for your time and attention. Please do not hesitate to contact us for any question and suggestion.